That makes Mondays just a tad better. Sure, don't even say that around me.
Alright, let's get started here. Page 180, 181, implicit differentiation. There is some on that one website, some practice. There's not a lot in the book other than these right here. So, I mean, they're pretty easy to make up. All you need is put a bunch of X's and Y's together in an equation and then do the derivatives, you know. We will, on the gateway test, pretty much stick with ones that look like 15 through 22 there. Those problems, for the most part. So, you know, anybody got one of those that you want to see today? Which one? Number 20. Okay, got some fractional powers in there. The thing with 19 through 22 is you're actually supposed to find the value y prime. So they give you a point, so you do the derivative and then you plug the point in and you actually get a number answer. We won't do that on the gateway test. We'll do the part where you get down to find y prime. The key lesson for those that were gone, and just to review for everybody, is let's take one even a little simpler than number 20 maybe, just because of the fractional powers, at least to start here. Anybody got another one? 21. Okay, let's take a look at 21. Not that it's really simpler, but I don't want to confuse the issue with the fractional powers here. It says 2 times the quantity x squared plus y squared all squared equals 25xy. Okay? Now, we're supposed to find y prime, or we're supposed to find the derivative of y with respect to x, or dy dx. I mean, those are all saying the same thing. All right? Now, in the end, it said find the equation of the tangent lines of the curve. You know, so again, before you can find the equation of the tangent line, you got to have a slope and a point. They gave you the point, so really what you need is a slope. And so you need y prime. Okay, so it's the same question. Find dy dx or y prime. Now, when I say dy dx, for you that are gone, we're gone on Friday, the key there is it's with respect to x, that x on the bottom. That's the secret. That x is the input variable and y is the output variable. And to summarize that, with respect to x, what's the derivative of x squared? 2x. With respect to x, what's the derivative of y squared? 2y times y prime. Because the difference there is the first one had x, I was doing the derivative with respect to x. The second one had y, the output variable, and I was doing the derivative with respect to x. And it comes from the chain rule. It's like I'm saying I got some stuff squared. Well, the power rule says you bring the 2 down in front, you leave the y alone, that's a 2y, and then you tack on the derivative of the inside. Well, what's the derivative of y? Y prime, or dy dx. So that's why we tack on this y prime. In this problem, we didn't tack on an x prime because what's x prime? X prime is 1. That'd be like dx dx. The derivative of x, if you thought of this as well, some stuff squared, you bring down the 2, leave the x alone, times the derivative of the inside. What's the derivative of x? 1. The derivative of x with respect to x is 1. The derivative of y with respect to x is y prime. That's the difference. Okay? So we would not tack on, we would not do that. So essentially what we ended up saying on Friday is anytime you do the derivative of a y, an output variable, you have to tack on the y prime. Or if the output variable was f, you tack on an f prime. And if the output variable was, p, you tack on p prime, whatever. So that's really the secret of this. So then the nuts and bolts of it, how you end up working it is you take a problem like this, you say, okay, now let's do the derivative of both sides. All right, so the derivative of this side, the 2 would just hang out. We'd bring that 2 down in front. We would leave the inside alone. We would drop that to a 1. We would multiply by the derivative of the inside, which would need a set of parentheses. And what's the derivative of the inside? 2x, 2y, y prime. Equals. How do we do the derivative of 25xy? Product rule. You should think of this as that. Think of it as 25x, put the 25 with the x, 25x times y. It's two different functions of x. We've got to do the product rule. Derivative of 25x, 25. Leave the y alone. Plus 25x left alone. Derivative of y, y prime. Okay? Now what was our next job? Get the y primes together. Now usually that just meant subtracting stuff over from one side to the other. Problem here is we've got a multiplication here. Okay? So this is where this one gets a little bit longer. We've got some algebra to do. Well, we can't just start subtracting stuff over. I got to get this y prime, and I'm not going to put that 1 there because that just confuses. It looks like it's a prime maybe. So we got to be careful of that. But I've got to get the y prime terms together. So probably about the fastest way to do that, or easiest, is going to be to FOIL that out. Because I got to get a group of terms. There's really no other good way to get this y prime together with that y prime. Okay? So I would say I'm going to leave the 4 out of it for right now. X squared times 2x would be 2x cubed. Outers would be 2x squared y prime. Inners would be 2xy squared. Last times the last would be 2y cubed y prime. Okay, then all those will have an 8 on them, right? Because I'll multiply by a 4 now. Then I got 25y plus 25xy prime. Okay? So I'm going to have 3 terms. So now when I distribute that 4 through there, these will all become 8s. Okay? And now I'm going to go ahead and leave my y prime terms on this side. Subtract this one over. Okay? Now, for this particular problem, 21, I haven't really looked at it. The point 1, 2 is there. I could have, right at this point, for problem 21, I'm kind of thinking of the gateway right now. For problem 21, I could have taken a 1 in for all the x's, and I could have taken a 2 in for all the y's right here, right? And probably simplified this work. Does that make sense? Wouldn't that have made it a little easier? Because I'd have had 1 plus 4 is 5, 5 times 4 is 20. Here I had a 2 plus a 4y prime. I mean, I could have done some things, made number 21 a little easier the way they asked it. But on the gateway test, the question is going to be find y prime. So that's why I'm going through all this. All right. So I've got this y prime term and those 3 all on that side. On this side, I'll have my 25y. Subtract over my 8x cubed and subtract my 8xy squared. Now what? Take out a y prime. Right? That's the whole point of getting the y primes on one side. So I get 8x squared y plus 8y cubed minus 25x. And then I got all this stuff here still. And then what? Divide. So now I get y prime equals, and then there you go. Okay? And then I'm not going to go through the rest of it right now just because that's just plugging in numbers and adding, subtracting, dividing, whatever. So you can go through that. So the final equation came out to be, well, you had it in the back. What was it? What did they get for the slope? 2 11s. Where at?
But I'm asking if that would eat the.
Come on over there, but you're writing a y.
Yeah, I'm writing the answer to the equation. Yeah. So on 21, so it came out to be 2/11 for the slope. And then you'd have x minus 1 plus 2 like that, right? So there'd be the okay. But like I said, on the gateway test, we'd be looking for this final answer right here, your y prime. This one was harder because of the multiplication in the beginning. Now, something you could have done is you could have FOILed this out first, right? We could have done some algebra here. We could have FOILed this out and got it just as a group of like 3 terms or 4 terms here. And then had this on this side, and then you wouldn't have had to do all this foiling at the end, on the back end. Okay, I think it'd have been about the same amount of work. Okay. Now the gateway test, if I had all that amount of work, that's pretty hard. So if that's one of the 3, kind of hard ones that you might have it. The easier ones would be ones like 15 and 16 and 17. Huh? Those would be the ones. Those would be the ones that don't have, that foiling, all that extra algebra. Yes.
Would that be as far as you want us to go, as far as simplifying when we get to that after dividing?
After you get to here?
Yeah.
Yeah, I think so, because I'm not sure there's anything that factors out. I'm not sure they have a common factor. You know what I mean? I mean, sometimes there's a common factor you can take out and cancel. Simplify, yeah.
Can you write that y? What they did in the book is they wrote that y prime as dy over dx. You can
Yes.
do that too.
Same thing, right. Y prime and dy over dx are interchangeable. Yep, they're exactly the same thing. All right, on 20, somebody asked about 20, so let's take a look at that one. The only difference, or the main difference, I guess, is because you get some of those fractional powers in there. But it's, again, what I want you to know about implicit differentiation is when you take the derivative of something with a y and then you tack on the y prime, the output variable, doing the derivative with respect to x, you're going to gather the y prime terms. After you do that, you're going to gather the y prime terms on one side, and that way you can factor out a y prime and divide, and that's basically what the problems I'm going to give you on the gateway test will look like. So if you've got x to the 2/3 plus y to the 2/3 equals 2, when you do this derivative, you get 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3 times a y prime, right? When you do the derivative of y, you tack on a y prime. Equals 0. Don't forget the derivative of 2 is 0, the derivative of a constant. So now there's only one y prime term. So now we can pretty easily get it by itself by just subtraction. So we subtract that over. We divide, well, the 2/3 are going to cancel, right? So we divide by y to the negative 1/3. We get a negative x to the negative 1/3 over a y to the negative 1/3. And I would even accept that. I mean, now I know on this one you're supposed to plug in the 0.11. Well, that's nice because 1 to the negative 1/3 is just 1, and 1 to the negative 1/3 is just 1. And so you end up with -1 for the slope. Okay, I mean, so they gave you nice numbers to plug in. Now you might say, well, you don't like those negative powers, so you'd rather flip the y up top and that to the bottom, and that'd be fine. Right? You can do that, rewrite it. That's just rearranging, and I don't care too much about that. So if you just left it like that, that'd be fine. All right? So that's implicit differentiation. What I'd like to do right now, and if you want to just get some scratch paper in your notebook or whatever, is throw out a few, just a handful, maybe 3 or 4 problems, just some general derivative practice for the gateway test. We've got one more set of rules to go, like 3 new rules. We've got to talk about the inverse trig functions and just inverse functions in general. We're going to do those here a little bit. But let's just throw out a couple of problems for you to try, like what we've learned so far. Okay? Well, let's start with one of these implicit differentiation. So when I say you can make up your own for practice, and since I showed you on the calculator where it will, it'll give you the answer, where you can type it in. I mean, you can just make up your own and try it, and then use a calculator to check, see if you got it right. And what I would typically do is I'd make something that's got maybe an X term only. Maybe something that's got an X and a Y term in it together. Okay, that could be even let's square that X. Let's make it 4X squared Y maybe. Plus maybe just a Y term. And then a lot of times you just have a constant term on that side, but you could have other terms on the other side too. Okay, go ahead and try that one. Find Y prime. That's the way the ones on the gateway test are going to look for the most part. Chances are pretty good they're going to look like that. This is called implicit differentiation.
No, turn around. Good for you. What'd you get? Well, I didn't get quite.
All right, did you remember the product rule in there?
Yes.
Okay. Now it's funny, we seem like 4x squared y, or I put a number in there, we remember the product rule. Sometimes you get a term that's just xy. You got to remember the product rule. If it's just an x and a y, no number in front or anything else. The other thing is, did you remember to distribute that negative? Or did you attach that negative with the 4? Because if you didn't, then you would have to distribute that. In other words, if I was going to do a product rule on this one, I would think of that as negative 4x squared times y. Because think about it, the product rule has a sum of 2 terms. You do the derivative first, leave the second one alone, plus the other one. Well, here you've got -4 times that, so you'd have to have -4 times each of the parts. But you can avoid that, having to worry about that, if you just attach the -4 to the x squared. Okay? So it should look like 6x. When you do the first derivative, it'd be -8x, leave the y alone. Then you would have -4x squared times the derivative of y, which is y prime. And then plus 3y squared y prime, and then 0 over there. So it should look like that. And again, that second and third term should both be negative. If you miss that, that's enough to miss it, right? When it comes to gateway count.
I have plus a -4.
Plus a -4, same thing. So the first step looks like that. Now usually if we can get that part right, we're most of the way home. The rest is just algebra. Although we make plenty of algebra mistakes too. So that's a lot of what we're practicing here when we do these as well. So we got two y prime terms, so we should leave them on one side, move the others over. Remember when you move them over, you change their signs, right? Subtract them over. Take out the y prime. Okay, now sometimes when you type in your calculator, it may factor out a negative or something because it wants to write it a different way, but we take out the y prime, and then we just divide. And there really is nothing we can factor out, nothing to cancel or anything.
So one of the negatives you can
Those negatives would not cancel out, no. The only thing that can cancel is a factor. You can only cancel factors in a fraction, which means you'd have to factor something out. Okay, when we reduce 6/8, the reason we can factor out or we can cancel a 2 is because 2 is a factor of the top and 2 is a factor of the bottom. Right? We can't reduce 5/7, and I don't care if you write it, 5/7 does not reduce, but some people, if I wrote it 2 plus 3 over 2 plus 5, some people would want to cancel those 2's.
Yeah.
Right? And say that 5/7 is the same as 3/5. Well, it's not. And you can't cancel the 2's because 2 is not a factor of the top and is not a factor of the bottom. Okay? So that's the difference. Okay? If you want to take out a negative and cancel them, you can do that. And I would guess, to be honest, my guess is in your calculator they would do that. They would probably take a negative out of the top and make it 6x minus 8xy. Take a negative out of the bottom and make it 4x squared minus 3y squared. And then cancel the negative out of the top and the bottom. So if you type that in, it wouldn't surprise me if your calculator came out with this answer. Okay? But that you won't have to for the gateway. All right, let's try this one. Y equals sine x over 1 minus cosine x. Now, is this implicit differentiation? No, right? Implicit differentiation is going to be very easy to spot. It's going to be a mixture of x's and y's all strewn about. This is just y equals function of x. This is just what 8 out of the 10 on the gateway test are probably going to be. You're going to have 1 or 2 maybe implicit differentiations. The vast majority will be straight product rule, course rule kind of stuff. Okay, go ahead and try this one.
Yeah, I did. Surprise.
Oh my god.
Popo. I love it. I
The
love it.
derivative of negative cosine is just sine, isn't it?
No, that,
What? Because cosine, the derivative of cosine is negative sine. Oh, wow.
Negative cosine would be negative.
Right, opposite.
No.
Yes. Look right here, cosine equals negative sine, the derivative. So negative cosine, get your card.
What?
The derivative of negative cosine would be positive sine, right?
Derivative of negative cosine would be positive sine. That's right. No, I shouldn't.
Huh.
Yeah, so it's minus
Okay, so a cosine over a negative cosine would then cancel out.
Say that again.
Cosine over a negative cosine would cancel out. What? Okay. Quotient rule. U over v. So finds u 1 minus cosine of v.
yeah,
It's u prime times v equals minus u times v prime all over v squared.
alright, little hint here. There is some algebra and some simplifying you can do here. And in this case, yes, you have to. Now, a couple things about the simplifying. First of all, it happens most of the time in the quotient rule. And because that's when you have a fraction and that's when you're going to potentially have something that can factor out, get canceled, and so forth. The other thing is it happens most of the time when you have the same type of function family on the top and the bottom. That's when it's most common. Now, if you get like an e to the x over a cosine x, a lot of times a mixture, like of an exponential and a trig, a lot of times there isn't anything that cancels or anything. But this has trig on both, so that's kind of a hint that you might. Okay? And again, I'm throwing some of these out here because these are ones we tend to have the most trouble with. That doesn't mean you're going to have 10 of these on the gateway test, right? I think I said the other day that maybe there'll be 2. If there's more than about 2 or 3 where you feel like you're doing trying to do a bunch of simplifying, you're doing too much, right? You're overthinking. All right. Now, in this one, let's just go through the basic quotient rule first of all. The basic quotient rule here would say derivative of the top, which is cosine, times the bottom left alone, right? So derivative top cosine times the bottom left alone minus the top left alone sine and the derivative of the bottom. Well, the derivative of 1 is 0. The derivative of negative cosine would be positive sine. Right? All over the bottom square. Now, first of all, I would not FOIL out the bottom. Remember when we were doing limit problems and we were talking about conjugates, multiplying by conjugate to get common denominators? And I always said don't multiply out the bottom, but you might multiply out the top to see if some terms can combine and zero out and whatnot. But the bottom, I would leave that 1 minus cosine because what I'm hoping in the end is I can factor and cancel. So the bottom's already in its factored form. So I'd want to leave it the way it is. Now in this one, I can already see I've got a big set of parentheses right here. Okay, I've got a set of parentheses here, and if I would distribute that, I would get a cosine squared. And right here I get a
Sine squared.
and anytime I see a cosine squared and a sine squared, I'm thinking maybe what? Cosine squared plus sine squared is 1. Now, it doesn't always happen. Sometimes we try to make it happen when it ain't going to happen. If you get a cosine squared minus a sine squared, that's not going to ever turn into a 1. I don't care how many negatives you try to pull out, you can't turn a cosine squared minus sine squared into a cosine squared plus sine squared. Can't happen. Okay? But I think that could happen here. I get a cosine x minus a cosine squared minus a sine squared. Now, a lot of you, I think, stopped right here. Or many of you may have stopped right there. Okay? And the only thing that would stop you from that is recognizing the sine squared and the cosine squared as possibly being a 1. Now, the fact that they're both negative is good for simplifying, because I can take out a negative and then they both turn to positive. And then you end up with cosine squared plus sine squared. So I got cosine x, and I'm going to take out a negative of those two. It ends up being that. So cosine x minus that quantity, and that quantity is just 1. So now I get cosine x minus 1, and on the bottom I have 1 minus cosine. Now those can almost cancel. We had a limit problem one time. They had 9 minus x on top and an x minus 9 on the bottom. What do you got to do to get those to be the same? Take out a negative. So I've got cosine x minus 1 here. If I take out a negative, that turns into negative cosine x plus 1, which of course is 1 minus cosine. So this negative would stay on top. This 1 minus cosine would cancel one of those, and I'd end up with that in its simplified version. Okay? So yes, on the gateway test, you would need to do that amount of simplifying. Okay, so see a sine and a sine squared and a cosine squared. See if there's some algebra that possibly make that reduce down. Sometimes it's not going to happen, but I just picked one where it did work pretty nice. Okay? Right here I had a 1 minus, when I took out the negative, that made a 1 minus cosine. And down here I have 2 1 minus cosine. So I canceled one. So that's why there's only one down there. Okay? It's kind of like having an x over an x squared. Cancel the x. All right? Okay, let's stop right there with that. We'll see how much time we have towards the end, and we'll come back and maybe try a couple more. All right. We'll go get on the websites maybe and see if we have something we can look at on those. All right, turn in your book, please, just to the next page, page 182.
That's 173.
182, please. All right. Now, section 3.4 deals with inverse functions. Now, you should have had some of this in advanced math, algebra 2 a little bit, mostly last year probably. This idea of inverse function. We just want to hit on kind of some basic properties of this. Okay, but our goal here is to end up with the derivative of the inverse trig function, sine, cosine, tangent. So inverse sine, inverse arc sine, arc cosine, arc tangent. That's what we want to end up with. Okay? All right. First of all, inverse functions have a couple of properties. One of the more famous ones we have, I had up here a second ago, it's the picture in your book on page 183 there. E to the x and natural log of x. And those are the ones in the darker blue. E to the x and natural log of x are inverse functions. Okay? Now if I start with y equals e to the x, and you look at that exponential graph, the one on the far left there, and then you look at natural log, the dark blue one there, you have that dotted line y equals x, and they're mirror images. So inverse functions are mirror images in that diagonal line. Okay, that's one property they have. Another property they have is you can interchange the x and the y. Okay, that's what inverse functions do. We interchange the input and the output. So the domain and range should be exactly flipped on two inverse functions. All right? Another definition we have for inverse functions is if we go, and I'm not going to write out the whole thing on page 182, but it essentially says is if f of g of x is equal to x and g of f of x is equal to x, then f and g are inverse functions. In other words, if you plug in something and get an output, and then you take that output, plug it into the other function, and get back to what you started with, they're inverse functions, and it has to work both directions. Now, a lot of people use x and x squared and square root as inverse functions, and technically they're really not quite. And we'll get to that in a minute. But if you take, but for this example, it works pretty nice. If you take 3 and square it, you get 9, and then you take 9 and square root it, you get 3. That's what we're talking about. So you put x into the g function, take that result, put it back into the other function. If you get x back, what you started with as a result, inverse functions, but it has to work both directions. And that's where that one falls apart a little bit. Okay? And we'll show that here in a second. That's the definition. So what that allows you to do is interchange the x, y. So if I want to find the inverse function of e to the x, I could put an x there and a y there. And then do what? Solve for y. So if I want the inverse function of e to the x, I can interchange, and actually this works for any function, interchange their x and their y's and then solve for y. Now unfortunately, we sometimes get problems where we can't solve for y. Okay? And so that causes a little bit of problem not being able to write it in function notation. But when I get to here, what would I do to solve this for y?
Natural log.
Do the log of both sides. So the log of this side is that. Log of this side is that, which would just be y. Okay? So we can see how we get e to the x and natural log being inverse functions. All right. If I gave you this function, f of x equals 2x plus 3, which is just a diagonal line, slope of 2, y-intercept of 3, and I said to write its inverse function. Now the notation we use for inverse is a little bit unfortunate. That -1 is kind of confusing. A lot of people think that means reciprocal. It's not. That's where with the trig functions we confuse sometimes. If you see sine -1, you think it's cosecant, right? Because you're thinking reciprocal of sine. That's not what it means. Sine -1. That's why I prefer to use arc sine. I'll usually say arc sine most of the time instead of sine inverse sine. They're the same thing. So -1 does not mean reciprocal in this case. It means inverse. Okay? Well, if this is what I'm trying to do, if I'm trying to find the inverse function of that f, what I would do is first write it as y equals 2x plus 3, and then do like we did over there. Let's interchange the x and the y. So for lines, for simple algebra type equations, this is a pretty easy process. Okay, my original function was y equals 2x plus 3. So on this one, I'm going to interchange the x and the y, and now I'm going to solve for y. So I get x minus 3 equals 2y, or y equals 1/2 x minus 3/2. Then I could write that up here as my inverse function. 1/2 x minus 3/2 would be my inverse function. And if you graph those two lines, they would look like mirror images of one another in that line y equals x. Now, something that you might notice about those two. That function and its inverse. What do you notice about their slopes? The slopes are reciprocals. Okay? Now those are lines. Now, of course, we know about opposite reciprocals. What kind of lines have opposite reciprocals? perpendicular, right? We're not talking about perpendicular lines here. Okay, so it's not opposite reciprocals, but their slopes are reciprocal. Okay? Now does that always happen? Well, if you look at your book there, okay, if we go to the next picture, if you turn to page 184, that actually does happen. Okay? So if you, and now this is where, of course, that's going to connect to derivatives, right? Because derivatives are slopes, right? So here's the key. We're going to be talking about derivatives of inverse functions. They are reciprocals. Here's two lines. We can see they're mirror images, so they're inverse functions. Okay? And it kind of makes sense that their slopes would be reciprocal. You start looking, if you interchange the input and the output, doesn't it make sense you'd be interchanging the rise and the run? Okay? Because the run is the difference between the x's, the rise is the difference between the y's. So if you've interchanged those, you ought to have just flipped over the rise versus the run. So they should be reciprocal. Okay? So hopefully that makes sense as well. All right, let's talk about this theorem in the middle of page 184. All right. So theorem 5, you might want to write this one down. And this is something we'll use again later on, and this is a question that comes up a lot in the multiple choice part of like our midterm, AP exam, final exam. It says, if f and g are inverse functions, okay? If f and g are inverse functions, then g prime of x is equal to 1 over f prime of g of x. If f and g are inverse functions, then g prime is equal to 1 over, there's that reciprocal idea, it's 1 over f prime. In other words, it's like saying that the slope of g is the reciprocal of the slope of f. Now there is this one difference. You notice that g of x is on the inside. The inputs have been flipped too, right? For the g function, we've got the input x. But for the f function, the input is g of x, the output of the g function. Now, you can see it in this picture on page 184 pretty easily, I think. If you look here, these two have reciprocal slopes, but they have them at two different points. This function has the slope at B. This function has that slope at point A, the output of the other function, because we've interchanged that. Okay? So they've got reciprocal slopes, but it's not like f prime of 2 and then 1 over g prime of 2. Right? It's not both at 2. And this picture shows it pretty well. Because of that mirror image, those inputs and outputs have been flipped. So you get this right here. Now, where does that come from? You don't have to know this unless you don't think you can memorize this. Okay? Now, you're not going to have to memorize this for the gateway test. Obviously, we don't need that for that. But later on, we'll be using this. But here's where it comes from. If f and g are inverses, think about what we just said a minute ago. F of g of x has to equal what? If they're inverses, has to equal x, right? What you put in has to be what you end up getting out if they're inverse functions. Well, let's do the derivative of both sides with respect to x. What would you get on this side? F prime, leave g of x alone, times g prime of x equals 1. Well, now it's pretty easy to see where that comes from, right? If you start with the inverses, this should be a true statement. You do the derivative of both sides, you just divide over f prime of g of x, and you've got that rule right there. Okay? So it comes from this idea right here. But basically the lesson is they have reciprocal slopes, and on one function it'll be at the point, say 1, 7, on the other function it'll be at the point 7, 1, because their x's and y's have been interchanged. Okay, so that's the idea of reciprocal slopes. Let's take a look at that with x squared and square root of x. if I start with, to get back to here. Okay, so that's where that comes from. So if I start with f of x equals x squared. Okay, what's the domain of that? All reals. Okay? So the domain of that is all reals or negative infinity to infinity. The range is what?
All reals are positive.
Greater than or equal to 0, right? So the inverse of that should have the domain and range flipped around. Now, most people would think the inverse of this is what? Square root of x, right? What's the domain of square root of x? X has to be,
Greater than or equal to 0.
well, that makes sense. That's the range. If we're going to flip the domain and range around, then that would be a match, right? What's the range of square root of x?
All reals.
All positives.
Square root of x is just positives. Now let's look at the graphs of those two. What's the graph of x squared? Parabola. What's the graph of square root of x? The top half of a sideways parabola, right? So x squared and square root of x are inverse functions. If I was to put square root of x on the x squared graph right here, you can kind of see how they're mirror images, but only for the right half of the parabola. Okay? What if I would have flipped and made it a sideways parabola? It's not a function. What happens is, and this is something called one-to-one functions or horizontal line test. If you have a function like a parabola, guys, if you've got a function like a regular parabola, if it doesn't pass the horizontal line test, when you flip it in that diagonal line, reflect it, it's going to fail the vertical line test. Does it make sense? Okay? So what you have to do for a function to have an inverse, it has to not only be a function, pass the vertical line test, it has to pass the horizontal line test as well. So that when we do its inverse, it'll pass the vertical line test. The way we do that is we restrict the domain. So for this particular problem, we would restrict the domain to only the right half of the parabola. We don't need the left half, because it just repeats the same values that the right half does. See? So we'll just leave off the left half, and then when we do its inverse, that'll help us, that'll leave off the bottom half. Okay? So that way we get matching domain and range and the whole thing. Alright? So, I was saying that there was an issue with this f of x, g of x, f of g of x equals x kind of thing. If you put a 3 in and square it, you get 9. You do the square root of 9, you get 3. Seems fine. Now let's do it the other way. Let's start with the 9. Do the square root of 9, you get 3. 3 squared is 9. Okay, let's try that though with a negative 3. If you take negative 3 and square it, you get 9. If you do the square root of 9, you get 3. You don't get back to what you started with, right? You don't get back to the negative 3. That's why we have to restrict the domain to be just the positive. Okay? So that happens on a whole bunch of different functions where we have to do that. All right. Let's do this. If I do y equals x squared, let's do that interchange x and y thing and see how this shows up in this. If I've got y equals x squared as my original function, let's go ahead and interchange the x and the y. So that would turn into x equals y squared. And then we said we should solve for y, right? Well, when you solve for y, what happens? You get plus or minus square root of x, right? And so that's when you realize, so whenever that happens, that's when you'll say, okay, now I'm going to have to, if I just want a function, I'm going to have to restrict that. So you would say, well, I'm just going to take the top half. I'll just take the positive values. So I get y equals square root of x. So my y's are only positive, which then tells you, okay, in my original, I need x to only be positive. Okay? Because again, the x and y's are interchanged. All right, we're almost there. We're ready to talk about this idea of arc sine and what that means. So, when we solve a trig equation, we usually get down to this point. We get down to sine of x equals 1/2. And we usually stop right there and we just ask ourselves, where does sine equal 1/2? Where does sine have outputs of 1/2, right? And what's the answer to that question?
There's an infinite number of solutions.
Right? There's an infinite number of times when sine x equals 1/2. If you look at the sine graph, goes on forever and ever. Sine equals 1/2 right about there, right about there, right about there, right about there, and on and on and on. There's an infinite number of times when sine x equals 1/2. So how do we deal with that? Usually in the problem, the domain's restricted. We say look from 0 to 2 pi, or only look from 0 to pi, or whatever. Okay? Now, the step you don't normally do, you know, in algebra class you learn about subtracting both sides. David, knock it out, please. In algebra class, you end up with subtract 5 from both sides, divide by 10, you know, whatever. Do the square root of both sides, do the natural log of both sides like we did over there, right? Well, what you can do right here, it's a step we don't usually write, you can do the arc sine of both sides. Right? The way you undo multiplication, you do its inverse operation, you do division. You want to undo subtraction, you do the inverse operation. You add. You want to undo the sine function, you do its inverse operation. The inverse sine function. Okay? Or the arc sine function. So the step we don't normally write is this. Right? When you see arc sine 1/2, what that means is the same thing we always say on a problem like that is where does sine equal 1/2? Okay, this 1/2 is the input to the arc sine, but what we usually say in our head is where does sine have outputs of 1/2? And then of course we get pi 6th and those answers there. But now, if arc sine is a function, it should only have one output, right? That's what a function is. For any one input, it's got only one output. Well, we just got done saying that the answer to this question, right, is sine function at pi 6, you get out 1/2. At, where else? 5 pi 6? Is that another one? 5 pi 6, you get out a 1/2. And I was going to write those as ordered pairs. So if I flip the x and the y around, that means that when you put 1/2 in to the arc sine function, you'd have to get out all these different outputs, and of course then it wouldn't be a function. Okay? So for it to be a function, we restrict it to only this one answer, pi 6. Now the way that looks, if you turn in your book to the next page, you'll see a picture of the sine function, and of course the sine function is not 1-to-1. It does not pass the horizontal line test at all. I mean, the horizontal line would cut through there many, many times. So we just restrict it from negative pi halves to pi halves. That means we just look at quadrants 1 and 4. Quadrant 1 would give us the positive sign values. Quadrant 4 will give us the negative sign values. If you type in your, matter of fact, get your calculators out. Let's try this. Your calculator has this programmed into it. Okay? Now, before you type anything in, let me ask you this. If I would ask you, where does sine x equal negative 1/2, what would you have answered on that one? I think everybody would have come up with, everybody that gets the right answer would have come up with 11 pi 6, right? Because we just said sine is negative down in this quadrant, negative 1/2, that's pi 6, that's around here, that's 11 pi 6, right? That's what we could come up with. Okay, on our calculators, let's go to the trig menu and grab the inverse sine function now, sine negative 1, that's the arc sine. and then put in 1/2 and hit enter. You get pi 6, right? That's what we expected. Okay, now go back in and change that to negative 1/2. You don't get 11 pi 6, do you? You get negative pi 6. That's the same thing, isn't it? When you draw your unit circle, that just goes backward, that's just going counterclockwise, and so that would be negative pi 6. But that's because of this right here, this restriction. We take the sign and we restrict it from negative pi halves to pi halves, so our inputs for sine would be in there. That means our outputs then for the arc sine are going to be between negative pi halves and pi halves. Okay, they're going to be in quadrants 1 and 4. The positive ones will be quadrant 1, and the negative ones will be down here in quadrant 4. All right, in cosine, if we want to do this, and the same thing would happen with cosine, look at the next picture in your book. We're going to restrict cosine from 0 to pi, because cosine is positive in quadrant 1, and cosine is negative in quadrant 2. So that'll give us the positive outputs and the negative outputs we need for cosine. Okay? So we just take one piece of the graph that gives us all those cosine values from negative 1 to 1. Alright? Now remember, arc sine, this won't be on the gateway test, but on our next, on some other type of quiz or something we do, if I ask you what's arc sine of 3/2, what's arc sine of 3/2? What would you say? Okay, sine and cosine can't have outputs greater than 1 or negative 1, right? The outputs of sine have to be between negative 1 and 1, which means the inputs of arc sine have to be between negative 1 and 1, right? Again, that's that interchange the x and y, interchange the inputs and outputs. So just remember, sine, you plug in angles like pi 6, pi halves, get out values from negative 1 to 1. For arc sine, it's the reverse. You put in values from negative 1 to 1, and you get out angles like pi 6, pi halves, and that kind of thing. All right. So that's, again, not things that will be on this next gateway test, but things that we will come back and revisit as we go through and into these other parts of using these functions. So let me ask you this question right here then. Sine of, go ahead and write this down, sine of arc cosine what is the sine of the arc cosine of square root of 3 over 2? And these are problems I know you did last year in advanced math. What is the sine of the arc cosine of square root of 3 over 2? Well, we start on the inside. Okay? Now, arc cosine of square root of 3 over 2 is what? When does cosine equal square root of 3 over 2? That's pi over 6. So one way to do this problem is to then do the inside first and realize that arc cosine of root 3 over 2 is pi over 6. You can draw a triangle if you need to. We're going to do that in a second here. And what's sine of pi over 6? 1/2. Okay, so that's nice when it's a value is something you know. Now let's try this one. Sine of arc cosine of 3/5. Sine of arc cosine of 3/5. That didn't work either. Okay? Sine of arc cosine of 3/5. Well, again, you start on the inside and you say, well, what's the arc cosine of 3/5? Well, about the only way to do this is to draw a triangle. What's the angle whose cosine is 3/5? Well, SOHCAHTOA, adjacent over hypotenuse. because 3/5 is clearly not one of those special angles that we've memorized. So you get 3/0, right? This would be think about this now. Arc cosine is saying what angle does cosine equal 3/5? Well, it'd be this angle right here. And then we don't need to know that angle though. What we want to do is the sine of that angle. Well, what's the sine of this angle? It's the opposite over the hypotenuse. So all we need is to get this. Well, it's a 3, 4, 5 triangle. So Pythagorean theorem tells us that's a 4. And so the answer to this is 4/5. So we didn't need to know what that angle was. What we need to do is be able to draw the triangle that represented that angle and then be able to get it from there. Okay. If you remember on that derivative rule sheet that I had up the other day, I think I've still got it here. No, I don't. Okay? Well, I had the derivative rule for arc sine up there. Okay? And it was this. The derivative of arc sine of x is, it wasn't x actually, it was u. We had a u written in there.
Yeah, it's like 1 over radical something.
Change that to a u. It's 1 over the square root of 1 minus u squared times u prime. 1 over the square root of 1 minus u squared times u prime. Okay, that's it. Now,
Prime is just the change.
that's just the chain rule. That u prime out there is just the chain rule. You guys were gone Friday. We kind of rewrote our derivative rules using u, but that just was the chain rule. Because usually there's something inside that arc sine function. Now, many times they'll put the u prime, just stick it up on top, but I put it off the side just to emphasize that's just the chain rule. Something you kick out at the end, the derivative of that. All right. Now, where does that come from? Well, it comes from this right here. Let's write, let's let f of x equal sine x, and let's let g of x equal arc sine x. Okay? F of x equals sine x, and g of x equals arc sine x. Right? And we're going to use this thing here, which remember, this just came from the chain rules, is just where this came from. All right? So I got g, so g prime of x, which is what I'm interested in, right? I'm interested in what the derivative of arc sine of x is. So g is arc sine of x. So according to this rule, g prime should be 1 over, because sine and arc sine are inverses, with a restricted domain, right? As long as we restrict the domain property like we showed earlier, they are inverses. So this would be 1 over what? F prime would be cosine with what inside? Arc sine. Okay? So the derivative of g, with f and g being inverses, because of what we learned earlier today, with f and g being inverses, g prime, which is what I'm interested in, the derivative of arc sine, should equal this. Now you say, well, what is that? Well, let's take what we learned last year. Okay? What's arc sine of x? Well, that's the angle whose sine is x. Wouldn't that angle right there be the angle whose sine would be x? Opposite over hypotenuse, right? And we want the cosine of that angle. So the cosine of that angle would be adjacent over hypotenuse, correct? So I need to know this leg. Well, how can we get that leg? Pythagorean theorem, right? This squared plus x squared equals 1 squared, right? Call that question mark. Question mark squared plus x squared would equal 1 squared. So the question mark should be square root of 1 minus x squared. Positive, because we know this is positive, right, in the first quadrant here. And that's where we've restricted our domain. So the square root should be this. So down on the bottom, the angle whose sine is x is this picture right here, and we want the cosine of that angle. The cosine of that angle is this over 1, which is just that. And so that is where that comes from. Will you have to repeat that again? No. Okay? Well, there is no u. The u is x. So the derivative, what's u prime? What's the derivative of x? 1. So if your function is just arcsine of x, this is the derivative. If the derivative is, if you want to do the derivative of arcsine of 2x, well, let's, hang on, we'll do one. Okay? All right, so let me give you this one. All right, so do this on your paper. Y equals x cubed arcsine of e to the x. Find y prime. Found it. So first and foremost, it's a what? It's a product rule, right? You won't have to worry about an arcsine derivative until the very end, right? Because in the product rule, you've got this function times this function. So the first part's very easy. Derivative of the first thing is 3x squared. You leave the second thing alone. The arcsine e to the x we leave alone. Plus the x cubed left alone times the derivative of arcsine, right? So everything up until here is nothing new at all, right? If I'd have given you this one on Friday, you could have written all of this down until here and then stopped and said, wait a minute, I don't know how to do the derivative of arcsine, right? Now, many of you wouldn't have written anything down, as you didn't, as I gave you this, and you paused and said, wait a minute, what, arcsine, I'm confused. Well, really, you shouldn't even have thought about doing the derivative of arcsine until you get to here, right? You first should have looked at it and thought product rule. All right, now I'm ready to do the derivative of that. Well, what's the rule say to do? The derivative of arcsine of u is 1 over square root of 1 minus e to the x squared. What's e to the x squared? That's e to the 2x. Now, if you wrote e to the x squared in here, that would be fine. I would not count off if you even left it that way. But that is e to the 2x. Anytime you have a power on a power, you can multiply the powers. So you could write that as e to the 2x. Times the derivative of its inside. The derivative of the inside is e to the x. Then you look at it and you say, well, yeah, I could put those two on top and that'd just be rearranging. So to be honest, on the test, you could stop right there. Okay? You could put the x cubed, the e to the x up on top and make it look a little nicer or whatever. Make that be e to the 2x in there. Now, understand that you almost never can do anything with that square root of 1 minus u squared. Rarely, I mean, you certainly can't make that 1 minus u, you know, like square root the 1 and square root the u squared and that kind of stuff because of the minus sign. So rarely is there anything that happens with this that you can simplify. Unless there ends up another square root on top and, you know, depending in those cases. But most of the time, there's not a lot that happens simplifying wise with them. All right, so let's go ahead and write the other two rules. Arc cosine so if you've got arc cosine of some stuff, so at this point now again, I think it was important for you to understand, for us to review this idea of inverse functions. That's all important stuff we have to do. Midterm, gateway, or midterm, final exam, AP exam, all that stuff. There's going to be some inverse things. We're going to have to come back and deal with these again. And where this comes from, and this little theorem right here, and this reciprocal slope thing of inverse functions, important stuff. But for the gateway, simply understand if you see arc sine of some stuff, that this is the rule you follow to do the derivative. If you see arc cosine, it's exactly the same, except it's a negative 1 on top. It's exactly the same, except it's got a negative 1 on top, which fits the pattern of what we've done before. The cofunctions are negative. The derivative of cosine is negative sine. The derivative of arc cosine has a negative on it. And then the other one we will do is arc tangent. And that is 1 over 1 plus u squared times u prime, and there is no square root on that one. There is no square root on arc tangent. Okay? Alright, so let's go back to what we were doing earlier where we tried a few of the problems here. So let's go, remember on my website, I've got these two links for some practice problems. Oops, that's not the one I wanted. For those of you that weren't here Friday, I showed these two links that I have. One says practice derivative problems, one says practice derivative tests. If you go to the one that says practice derivative tests, it's got test 1 and test 1 with solutions, test 2, test 3, and then an actual test that they gave. Test 3, I think, either test 2 or test 3 has some implicit differentiation ones on. That's about the only other place to get implicit differentiation practice unless you just make up some of your own. Okay? I think there's some inverse trig on there as well. But the other link says practice derivative problems. This is where you can have it crank out some of your own. So let's go ahead and click on inverse trig and see what it'll give us. Let's go to difficulty 3. Oh, those are easy. Well. Ooh, some of those aren't very easy. Some are really easy.
Show it the right now.
They're either really easy or just almost ridiculously hard.
What's a sine? A cosine? Oh, it's just.
That's a new thing we're learning.
Yeah.
There's a good one right there. Okay, let's forget the cube root on this one. And let's just do x to the -2, x to the, this is y equals, x to the -2 plus arc cosine of square root of x. X to the -2 plus arc cosine of square root of x.
Yes.
All right. Now, you would have -2 x to the -3, right? Plus, arc cosine is -1 over the square root of 1 minus square root of x squared would just be x. Right? Now you could write square root of x squared. That I would call obvious simplifying. Square root of x squared, you would need to reduce that to an x. Times, then you have to do the derivative of square root of x. X to the 1/2 is 1/2 x to the -1/2. Okay? Now again, that would be enough for this problem because anything you do would be some rearranging. You could, the 2's on the bottom, you could put it out in front of the square root. This could go down on the bottom as a square root, as an x to the 1/2. You can move that to the bottom, but all of that would just be kind of rearranging things and not necessarily putting it together. Now, I changed this problem. It originally had that function.
The cube root.
Originally, it was a cube root of all that. Well, what would you have done? What would this part have been? This would have just been the derivative of the inside, right? So you'd had all that to the 1/3. So you'd have brought the 1/3 down in front. So you'd had a 1/3, all of that to the -2/3 times, and then that. And then this would have all then been in parentheses tacked on. And even then, there wouldn't have been anything you really could have done with all of that stuff. Okay? This part just would have been the derivative of the inside. All right. So, oh God, it's Monday, isn't it? They got a long way left. We better get going here. Get the assignment. Now, I'm changing the sheet just a little bit here.
Yes, please be less.
No, it's just different.
Oh. Well, that's not that bad.
Maybe he's gonna give us that.
Or maybe he was going to give us more until it's our turn.
Okay. Still 1 through 6.
Good morning. I just have one quick announcement before the seniors head to lunch. The academic competition team will not meet today. You will instead meet on Friday during lunch. Thank you.
So great. So how?
Okay, so it's probably technically a few more problems, but 1 through 6, which is just a little bit of practice of just some of that trig values, understanding arc sine, what happens, pi 6, that stuff. 13 through 24 are just trig with these 3 new rules, or derivatives, excuse me, with these 3 new rules. And then get on those websites and practice, or if you don't have easy access to the internet or whatever, then I told you on page 195, there is like 75 questions, a whole big mixture. Now listen, Wednesday is the gateway test. You can, if you want to take many gateway tests, wait and practice like Tuesday night. But hopefully you've already been on there, you've already been practicing some of these. Get working on those. Get working on those. Wednesday will be the only one we take in class.
I thought when in Minnesota there's like a collective gasp. But it was just a single gasp.
Mr. Clark, is there a way to limit the range on the calculator?
The range?
Yes. I'm trying to draw it out. That's really what I'm doing.
You could do, I think you could do a compound inequality. So you would do this one greater than and this one less than. Like what is this value?
Those are just two separate lines.
Right.
Like I've got this line, and if I clear that out, that line's just gone.
Right.
This is what I'm trying to limit the range. That's where
See, but these are both in the F1, right?
it doesn't like. It's not going to control me again.
Where do you have them? Where do you
They're
have
up in line.
Oh, there.
But it doesn't like to go from 99 to 1.
See,
I also had a problem on the homework where I couldn't